Okay, we'll get started with continuing on these addition reactions to carbonyls. We had left off on weak nucleophiles, and so the one we finished on was the cyanohydrin reaction. So I want to review that in sort of prelude to making amino acids, how they're made synthetically. So we saw that with oxidation state 2 functional groups, aldehydes and ketones. They can add weak nucleophiles, and one of them was potassium cyanide in the presence of a base under biphasic conditions. So again, the cyanide adds to the carbonyl, and then we get this alpha hydroxy nitrile. And so the important thing about that was the sp hybridized carbon of the nitrile is equivalent to a carboxylic acid. So I'm just going to write, so R CO2H, and that oxidation state 3 functional group equivalence is important synthetically for reasons we won't discuss too much in this class, but that cyanide anion is really one of the most common reagents to get carbon in a molecule at that oxidation state. And so the conversion of the cyanide to the acid is a hydrolysis, again using strong acidic conditions. So pretty much sulfuric acid, water, and heat, or strongly basic conditions, sodium hydroxide, water, and heat. And again, that's going to eventually bridge us into these carboxylic acid derivatives we'll study a little bit later in the module. So this reaction has a connection to another condensation reaction of a weak nucleophile. So we can take an aldehyde with ammonia, and that's going to form an imine. So we'll look at how that's done today, but to bridge the gap, we're going to study this reaction first here called the Strecker reaction. And this is quite common for making amino acids, so we'll study amino acids and then we'll dial back into how imines are formed. So the Strecker reaction is now going to form an alpha amino nitrile. Again, that prior reaction was alpha hydroxy nitriles. So overall, the reaction is making a formal equivalent of an alpha amino acid. And again, those are important biomolecules, which are monomers of peptides that make up proteins. So the conditions to do the Strecker reaction involve potassium cyanide, but now you're actually using ammonia as an organic solvent in water. So the ammonia will actually have preference for condensing with the aldehyde first to form an imine. And so an imine is a carbon-nitrogen double bond. So it's, carbonyl is CO double bond, imine is CN double bond. And again, so NH3, overall, if you look at what you're losing out of there, you're losing H2O. So we call that a condensation. And so nitrogen has the lone pair, just like the carbonyl group, that's delta minus, the carbon's delta plus. So the cyanide anion will attack that. And after a proton transfer, you get the alpha amino nitrile. And again, since the nitrile is equivalent to the acid, essentially that's what you're making, is an alpha amino acid. So I thought we'd spend some time on that before we get into actually how the imines and enamines are formed. So alpha amino acids, there's 20 proteinogenic, so those are naturally occurring alpha amino acids. There's a couple more that are more rare, but there's normally 20. And so, as we said, alpha again is the carbon next to a carbonyl. So alpha amino acid. And the way that the 20 of them differ is this side chain here, R1. So the naturally occurring amino acids have the S stereochemical configuration. And if we look at that in the form of a Fisher projection, the amine group is on the left, which gives it that capital L designation. So the conversion is, your eyeball is right here, and you're looking that way. So the amine group ends up on the left, the hydrogen on the right, and the R group down. So remember that naturally occurring sugars were D, naturally occurring amino acids are L. And as I said, they differ according to what R1 is, but they all have, I'll highlight it in red here, they all have the acid and then that amine residue. So the R1 is what's different. And so of those 20, there's 4 classes: nonpolar, polar, acidic, and basic. And that's how your organic text and your biochem text will classify them. Nonpolar is basically I'm trying to think of a way to generalize this. Basically aliphatic. I mean, you can have heteroatoms in there, but for the most part, it's going to be carbon without heteroatoms. Polar ones, you're now putting in like amine groups or hydroxyl groups. Acidic, those have a second carboxylic acid as part of R1, and then basic ones will have either amines or another functional group called a guanidine. So the names, these are the names, they are what they are. As you'll see on the next slides, they all have ways of being abbreviated. So there's the name, and then there's a 3-letter abbreviation, and there's a 1-letter abbreviation. And as you go further in the biological side of this, almost everyone uses the 1-letter abbreviations when they're talking about these things. Because as I said, they're the monomers that form proteins. And so if a protein has a couple hundred amino acids to it, it's just easier to write this sequence of letters. But you have to keep in mind that letter, how its structure is impacting overall the function of the molecule. So here are the nonpolar alpha amino acids. Glycine is the only one that does not have a stereogenic center. So the alpha carbon has 2 hydrogens. It's abbreviated GLY, and then the 1 letter is G. Again, the rest of them are going to have a stereogenic carbon at the alpha position, which is S. So alanine is ALA or A, and that's a methyl group. So we have a methyl. Valine is Val or V, that's an isopropyl group. Leucine is Lu or L, that would be an isobutyl group, so that's 4 carbons. Isoleucine has 2 stereocenters, and it's still a butyl group, but now it's a secondary. It's attached to carbon 2 of that chain. So methionine has a sulfur heteroatom, but notice that it's not a thiol, it's a thiol ether. So overall, it's more nonpolar than polar. So methionine, met or M, we can see the sulfur heteroatom in that chain. Proline, pro or P, is the only one that's a cyclic or secondary amine. And because of that, when you start learning about peptides and proteins, when you have proline in there in a long chain, that ring causes the chain to sort of kink or turn based on it being a secondary amine. Phenylalanine, Phe or F, has a CH2 group and then an aromatic ring. And then tryptophan, TRP or W, this ring here, this heterocycle is called an indole. And that's the chemical that's typically invoked, after Thanksgiving dinner when you feel sleepy. It's the tryptophan that's making you sleepy. So these are nonpolar. And so now look at the side chains of the polar ones. You're going to see amides, alcohols, thiols. So asparagine, ASN or N, has an amide in the side chain. Glutamine, GLN or Q, slightly longer chain amide, but that's the polar part of it. Serine is pretty popular. That's methylene and then OH, so SER or S. Threonine now has a second stereocenter with that alcohol. Tyrosine looks like phenylalanine, but the aromatic ring has a phenol. So remember that the hydroxybenzene was called phenol. And then cysteine, CYS or C, has a thiol. So that looks like serine, except now you have SH. And so all of these are pretty unique when they act as monomers in these biopolymers. They'll affect the overall properties of that molecule differently. So the 2 acidic amino acids both have a second carboxylic acid fragment. So aspartic acid and then glutamic acid. And so all of that chain length will eventually matter as you start learning about secondary and tertiary structure of proteins, about how these things can hydrogen bond with one another. That becomes very important as you move forward in those studies. So basic amino acids, look at arginine. This functional group here is called a guanidine. Histidine has an imidazole ring. That's this aromatic heterocycle. And we talked about nitrogen basicity. Even though both nitrogens are sp2 hybridized, it's that one that's more basic due to the location of the lone pair of electrons. And then lysine, which is lys or K, has a second amine at the end of its chain. So depending on the timing of the semester, we may revisit amino acids and basically their reactions between one another. So just to give you a brief preview of the issue that happens with that chemistry. How do I want to draw this? So typically, these are abbreviated AA for amino acids. So AA1, AA2. The bond between them, that amide bond, is generally called a peptide bond. So the reaction between them, if you wanted to couple glycine to alanine and make that specific peptide bond, so where the alanine amine is bonding to the glycine carboxylate part, the issue is they each have an amine, they each have an acid. So how do you selectively get that amine to bond to that acid? And so that involves selective protection of the different groups, so you only get that peptide bond forming. And again, the reason that's important is because, see the way I've written this, AA1, peptide bond AA2? If you can imagine, something like this, dot, 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 AA to the N, that's called the sequence. And the sequence matters. When you look at all the possible, say, constitutional isomers you can have, how you sequence them together ultimately affects the secondary and tertiary structure. So that involves some planning, but for the most part, that's all been figured out by humans. Nobel Prizes have been awarded for people that have done that. It's even now rendered to instruments that can do it automatically. So there's these fluid handling instruments that'll inject things at certain times, extract out, and then add sort of the next residue in whatever sequence you want. So computer algorithms and instruments have sort of figured that out, but it still remains for us to understand the logic of it. So what I thought I would do next is return to the formation of imines and enamines, that condensation reaction, and why they're useful. So we saw in the prior module how we get nitrogen into a molecule. We can use sodium azide, potassium cyanide, or this potassium phthalimide to get nitrogen into a molecule. But ultimately, those methods will result in the formation of primary amines. What if you wanted to make a secondary or a tertiary amine? And again, we want to make that specific molecule, not some derivative of it. So overall, what we're aiming to learn here in making higher order, so secondary or tertiary amines, is a process called reductive amination. And the key intermediate in that process is either the imine or the enamine. So we'll walk through imine structures first. So if you look at the 4 compounds listed, a way to think about it is this: the carbon that I'm highlighting in red. So again, that's your oxidation state 2 carbon. And really what those structures are coming from are carbonyls. So in the left 2, they're coming from aldehydes. In the right 2, they're coming from ketones. So if you sort of think this way, I'm going to slice that. And this can come from an aldehyde. And then the nitrogen part has to come from a primary amine. So overall, since it's a condensation, you're losing water. The O comes from the carbonyl, and then the hydrogens come from the amine. So the top part of that molecule already has 1 H, so it would need 2 more. So we would say that comes from ammonia. So ammonia plus butanol will condense. They'll lose water to form the imine. If you looked at the second one and did the same thing, what would the name of that amine have to be? So it already has a methyl group on it. You have to stick 2 hydrogens on the nitrogen, so that would be methylamine. And then you can do the same thing with ketones. So again, the key thing here is the imine comes from oxidation state 2 functional groups and a primary amine. So the nitrogen has to have at least 2 hydrogens on it. So this question we sort of already went through. The carbonyl species oxidation state 2 has to be butanol, so we can get rid of C and D. If we look at the top, we see there's a hydrogen there. It needs 2 more, so that has to be ammonia, so we can get rid of B. So in terms of the mechanism, so there's our aldehyde plus ammonia. We'll have the ammonia attack the carbonyl. And again, this is going to be equilibrium because ammonia is a weak nucleophile. One thing that most likely does not happen is the following. I'll draw it, and then I'll show you sort of a better way to think about it. We have to get rid of that oxygen, so we have to protonate it. So you never really want to show the oxygen itself abstracting a hydrogen in that way. And the reason for that is typically argued that, again, for that to happen, the oxygen lone pair has to attack that hydrogen from a certain angle. So everything we've learned about trajectories still holds true. And that's usually not favorable in an intramolecular fashion. So intra means within. So since we typically run these in the presence of water, we could even use water as a proton source. And show the proton transfer happening that way. And so that gives us a base, which we can now deprotonate that positively charged nitrogen. So that regenerates water. And now we can do an elimination of hydroxide. Which can do our last proton transfer. And one other thing as I've drawn it that I want to point out, so these are geometrical isomers because that hydrogen, as you see, on one of them it's drawn to the left, on the other it's drawn to the right. So you can actually assign cis and trans to that. So the one on the left, essentially you're doing the same thing as with alkenes. You have a lone pair that really doesn't get priority. So hydrogen gets priority. Then you look at the carbon atom of the double bond. Carbon would get priority there. Hydrogen gets priority too. So since the ones lie on the same side, that would be the cis. Or Z is the other term that's used. Then the other geometrical isomer would be trans, or E. So again, as we're past the interim of the semester, it's never too early to start thinking about the final. Those are things that you want to remember as you go into the final if you get sort of a nomenclature problem or something like that. But again, the mechanism is condensation. And what that means in this case is that water is generated. Condensation reactions can produce other small molecules. That's typically what they do. So as we'll learn later on in this module, like HCl is sometimes produced, but that's also called a condensation. So since these are equilibrium, the equilibrium is controlled by Le Chatelier's principle. Remember, where you can disturb it either by adding a lot of starting material that forces things to go to the product, or you can distill out the product as it's formed, or since you're also forming water, you can put in a drying agent that soaks up the water, and that shifts the equilibrium to the product side. So as opposed to imines, enamines still react with oxidation state 2 functional groups, but now you're starting with a secondary amine. A secondary amine is classified as only having one hydrogen. So really what you only have to worry about is primary or secondary amines. Tertiary amines do not do this chemistry. So an enamine is basically an alkene that is directly bonded to an amine. And so you just jam those words together, and that's how you get your enamine. So if you look at that sp2 hybridized carbon, you're sort of splitting there now. That carbon is the one that's at oxidation state 2, and we'll show why in this case you get the alkene forming. The difference between these, you can see the geometry. You have E versus Z. And these are both coming from butanal plus dimethylamine. And so they're constitutional isomers where the alkene geometry is changed. A complicating factor with ketones, if you look, do that slice. These are all coming from 2-pentanone. So there's now 3 possible products because for that ketone at oxidation state 2, you now have 2 alpha carbons. An aldehyde only has 1 alpha carbon. So we'll look at the mechanism of why now you're getting a double bond. So we'll discuss the factors of how those 3 arise, basically. Sort of the normal nucleophilic attack by the amine onto the carbonyl. We'll use water as the proton source. Then have the hydroxide deprotonate. So see the carbon with the OH in the amine? So it's still oxidation state 2, but now it's sp3 hybridized. When we had that sort of carbon with 2 oxygens, it was called an acetal. When it has oxygen and nitrogen, it's called an aminal. A-M-I-N-A-L, aminal. And so this is where the issue arises, is when the elimination happens. So that nitrogen lone pair comes down, and it's going to push out hydroxide. See that nitrogen atom, it no longer has a hydrogen to deprotonate. So a deprotonation has to happen from either of the alpha carbons. So if we deprotonate alpha, it doesn't matter which hydrogen. That's going to form the alkene. Nitrogen gets its lone pair back, and I'll say, just for brevity's sake, A, B, and C. So this, I'll draw it here. This would be path B. And now since alpha prime has 2 hydrogens, it does matter which is deprotonated. So those would be paths A and C, depending on the orientation of how that sort of side chain sits relative to the amine, whether you get the E or the Z geometry. And keep in mind when we talked about alkene stability, if we're using the amine as a substituent, A and C would be tri-substituted. And then B would be di-substituted. So since it's an equilibrium and you're probably getting a mixture, A and C would probably be more prevalent than B in there, but you're going to get all 3. So this mechanism really is how nature forms carbon-carbon bonds using enamines, because this happens under physiological pH. You don't really need strongly acidic or basic conditions. As you learn more about enzyme reactions, You know, those amino acids, whether they're acidic or basic side chains, they help shuffle the protons around. So here's something to think about. I'll start you off. You have a ketone, so oxidation state 2. You have a secondary amine. And what do you think the product will be? So that plus that firstly is going to form an enamine. And then when you look at those choices, which one is the correct enamine? So put another way, the alkene has to form between the oxidation state 2 carbon and an alpha carbon. So of these, choice B is going to be correct. So there's the oxidation state 2 carbon. There was the alpha carbon. If we sort of slice that bond, we can see that top half of the molecule is that secondary amine, which has to come from that molecule called pyrrolidine. So now that we've learned how to form imines and enamines, over the next run of slides here, we'll look at what can we do with them to form higher order amines. Before we get to that, just as a review, we have this molecule called benzonitrile. So it's a benzene ring with a nitrile. We're treating it with a strong reducing agent, lithium aluminum hydride. So it's going to reduce that sp hybridized carbon by adding 2 equivalents of hydride. And we're going to get a primary amine. This is called benzylamine. So imines and enamines both have double bonds, and we've seen already we can add hydrogen to double bonds. So reductive amination is a way of taking a carbonyl plus some sort of amine. You generate an enamine or an imine, and then you can reduce that, and you're going to get a higher order amine from what you started with. So an example of that, we see this imine here, and this came from, we have 5 carbons. It came from this ketone that was condensed with benzylamine, which we saw in the prior slide. So primary amine plus a ketone gives us the imine. we have that double bond which we can add hydrogen to. And so if you look at the conditions, the reducing agent is a derivative of sodium borohydride. So there's sodium borohydride, we saw that to reduce carbonyls to alcohols. This is called sodium cyanoborohydride. One of the hydrides has been replaced by cyanide. But also what's sort of weird or interesting about this, remember these hydride reagents are H-. So I'll put that in quotes. You're also running that in the presence of an acid, so trifluoroacetic acid. You would think, well, why doesn't the hydride just abstract the proton from the acid, generate H2, and then do nothing? The sodium cyanoborohydride is, the reactivity is attenuated enough that the reductant and the acid don't react with each other before anything else happens. So what first happens is the imine will abstract the acidic hydrogen from that acid. So I'll show it over to the right here. That generates this thing. So it's a positively charged imine called an iminium ion. And now that's electrophilic enough that the hydride reagent will come in and reduce it. So nucleophilic addition. And so overall, the acid provides one H, the hydride provides the other H to give you formally H2 that adds across that double bond. So just to point out, we started with a primary amine. We did the condensation to the imine. And if you look at the product, now that's a secondary amine. So that's what I mean by higher order. So I gave you the gist of that mechanism on the. Let me just dial back here to show you just how the arrow pushing would look different for an enamine. So sodium cyanoborohydride. Trifluoroacetic acid. So notice the position of the double bond. The amine at this point does not get protonated. Enamines have a significant resonance form. So there's our resonance arrow. Where the negative charge resides on an alpha carbon. And so what's nice about this resonance form is that it guides you in that, okay, that alpha carbon has to be protonated. So that's going to react with the acid. And now here you have an imine, but it's positive, so that's an iminium ion. And so now that sort of looks the same as before. Now the hydride agent can come in to do its nucleophilic addition. Nitrogen gets its lone pair back. And so you've done the reductive amination, and now you're ending up with a tertiary amine. Practically speaking, I can't remember, but you can put an indicator in here because you're starting with trifluoroacetic acid. You put some indicator in there that I believe is blue, and as the reaction proceeds, that blue color goes away, which is essentially telling you the reaction is complete. Prior slide. So I'll explain this, and then I'll dial back to the blank slide, and I'll show you how an enamine gets reduced so you can see that, because that's important for that reactivity. So in this table here, it's showing you what carbonyl species you can start with, aldehyde or ketone, the class of amine that you start with, ammonia, primary or secondary, what the condensation product is, imine or enamine, and then after you do the reductive amination, what you're ending up with. So ammonia will form a primary amine. A primary amine leads to a secondary leads to a tertiary. That's the logic. And so now, let's see where we're going here. So how can we use this in terms of a strategy? If we consider that this amine that's shown, so this is a tertiary amine. It has 3 different substituents, a methyl, an ethyl, and a cyclopentyl group. Basically, what you can look at is 3 ways of making this. If you're starting to focus your eye on the nitrogen, you can sort of break those bonds 3 different ways. And then each way is going to give you a carbonyl component and an amine component that you can do the reductive amination on. Let me see if I can remember that. So we'll set up a table here. So carbonyl and amine. So these would be what we need to start with in each scenario to do that reductive amination. So we'll say 1, 2, 3. We can do it 3 ways. And I'll just, I guess the way I'll start it is by sort of lowest carbon count. If we want to make this bond, that carbon atom, that methyl group, would have to be the carbonyl component. And then everything else is just coming from a secondary amine. So a 1 carbon carbonyl unit is formaldehyde. And then the amine component would be a secondary amine. if we wanted to do the other one, the ethyl, the carbon bonded to that nitrogen, that has to be that has to be now an aldehyde, 2-carbon aldehyde. And the amine component I guess that would be methyl cyclopentylamine. And then the third way, that one would have to start from a ketone. And the amine we would use would be this secondary amine, ethyl methylamine. And sort of the way that I sell this is, you've been through Gen Chem, you've been through organic. Maybe you like science, but you don't like it that much to become a researcher. Maybe you like business. Companies will hire people with scientific background, but are interested in business to figure out, okay, which route do we want to choose? Because now you have 3 different ways, and what you would do is a cost analysis of, okay, I want to make, a couple 100 kilograms of this. So what do these starting materials cost to do that? What's the cheapest way to do it, but also in considering if you have to move a lot of material around, what are the safety aspects? Formaldehyde is kind of a pain in the butt to work with. Acetaldehyde is, it's a low boiling liquid to my recollection. Cyclopentanone is a nice liquid at room temperature, so there's really no issues with volatility or toxicity or anything. Then you have this amine, which is probably a liquid as well. So this might be the best route. If you see these 2 amines here, that ring is probably the issue, getting a hold of that starting material, because you obviously have to buy it from someplace. And what is the cost of that versus the cost of this? So a science background, a business background, there are nice jobs that people do. Typically you get to travel the world because you're visiting these sites that make these things. Do they meet the quality you need? Because you don't want 80% plus 20% junk. You need to make sure that's as pure as it can be. Can you read the IR? Can you read the NMR? Are they giving you what they're selling you? That stuff matters. So here's an interesting one to think about. So I'll start you off here. You have an aldehyde, oxidation state 2. You have a primary amine. But now what's interesting about this, those 2 functional groups are connected in one molecule. So if they undergo all the chemistry that we just learned, what do you think the product is going to be? So the amine has to condense with the aldehyde. So since it's primary, that's going to give you an imine. The imine structure is C, but we're further reducing that. So we're doing the reductive amination. So the correct product is going to be A. Since we start with a primary amine, we have to end up with a secondary amine. And again, choices B and D are the distractors. If you just think of the functional group names associated with the reactions. At no point did we mention amide, which is B, or this other thing D, which is an N-hydroxyimine. So we never invoked that. And again, as you think about the final exam, those little bits of intuition will really help you eliminate distractors and funnel into the correct answer. Any questions? So the last 15 minutes, we're going to sort of switch gears and look at a different type of reaction, which is, as I said, eventually going to help us set the stage for getting into oxidation state 3 functional groups. This is still an addition to an aldehyde or a ketone. But now this type of addition is no longer reversible. So you get a nucleophile, it adds, it stays there, it's not leaving. And this specific reaction, it's known as a Wittig reaction. And so Wittig and Brown won the Nobel Prize in 1979. Wittig for phosphorus chemistry, and then Brown for boron chemistry as reagents in organic synthesis. So last week, the Nobel Prize in chemistry was announced. Does anyone know what it was for?
Wasn't it like the proteins? Did they use AI for?
Yeah, so this one guy and 2 other guys developed these AI programs that would basically model how peptides fold into forming proteins. So again, a big part of how proteins work is their shape, and their shape is determined by the amino acid sequence. And since the 40s and 50s, people have been interested in modeling that. And you can imagine prior to computers, it's like really hard, right? And so AI basically, I think of it as like software that learns how to think, and that's weird to, but these algorithms can sort of take known algorithms and learn from them. And the issue with these large peptides is there's so many like degrees of rotation and stuff. How do they come together and make a molecule with a function? And that's like extraordinarily difficult to predict, because there's all these different energy wells things can settle into. But they've developed the AI software that helps figure that out. So this is how far things have come nowadays. It's things have moved sort of from the lab environment now to in silico, within a computer, to do modeling basically. So the Wittig reaction, overall what it's doing is it's taking an aldehyde or a ketone and it's going to make an alkene. And to do that, we have to learn how to make the Wittig reagents. So there's 2 things that happen. The first is an SN2 reaction, where we have some alkyl halide. So again, it's got to be methyl primary or secondary to obey SN2 rules. And then we use this reagent here called triphenylphosphine. So notice phosphine. Phosphorus is below nitrogen. So nitrogens are amines, phosphorus are phosphines. So triphenylphosphine has a lone pair of electrons, just like nitrogen has a lone pair. So that's a nucleophile. The bromomethane is an electrophile, so the carbon gets attacked. The bromine leaves. And then you form this salt where phosphorus is plus, Br is minus. And what's interesting about this now is that carbon atom, those CH bonds have increased acidity. So that plus charge on the phosphorus next door increases the acidity a little bit. And so in the second part of this, we're going to treat that with a base. So for this type of reagent, we still have to use a pretty strong base, N-butyl lithium. And I'll draw these hydrogens out. There's the N-butyl lithium base. It's going to abstract a hydrogen. You lose butane gas as the conjugate acid. You get lithium bromide as a byproduct. And then this reagent here is called a phosphorane. And notice that carbon is negatively charged, so it's a nucleophile. The other thing that's important is see how the negative and the plus are next to each other. That species is also called an ylid, so a phosphorus ylid. And so the actual reaction after you make the Wittig reagent, that negative charge will attack the carbonyl carbon. A rearrangement occurs. I'll try to draw that on the next slide. And then what you end up with is an alkene. And I'll highlight in blue here that CH2 group. That ends up right here in that alkene. So the rest of the molecule in green stays the same. The driving force for this reaction is the production of this stuff here called triphenylphosphine oxide, because that phosphorus oxygen bond it's one of the strongest bonds, 544 kilojoules per mole. So you can take an aldehyde or a ketone and you make an alkene. So really what you should be able to do is look at any alkene the same way and come up with two different ways of making it. But let me just show you that intermediate that's formed. Because we want to understand how does the oxygen get out of that molecule. So there's the nucleophilic addition. So oxygen's minus, phosphorus is plus. We got 5 minutes. So I'll show this stepwise, but it can't happen all at once. So negative is attracted to positive. And so what's starting to look weird about this, phosphorus has more than an octet, but it can handle that again, because it's in row 3 of the periodic table, it can have an expanded octet. At this point, it's neutral, but what it's going to do is then extrude that triphenylphosphine oxide. So I'll say TPPO. So I'm going to show it sort of in 2 arrows like this, going down, and then this arrow coming up. And other people have come along after Wittig to show the intricacies of this mechanism. I've shown it pretty simply, but you know, if you had other substituents on this carbon in blue, then you can get different geometries, E or Z, and how these attacks happen, what trajectory, and how that 4-membered ring decomposes. That stuff matters as well in determining the geometry. So looking at cyclohexanone, so there's that oxidation state 2 carbon. We want to make that alkene, and the reaction, or the question is asking you, what alkyl halide should we use to make the Wittig reaction, or the Wittig reagent? So let's draw these out, and then we'll explain which one's correct. So there's 2-iodopropane, 2-bromobutane, ethyl bromide, and methyl bromomethane. So if we highlight in green these 3 carbon atoms of that alkene, that's telling us that the Wittig reagent has to have 3 carbons, and that the bond we need to form is at carbon 2 of that chain. So then we look at the choices, and we see that 2-iodopropane is going to be the correct answer. So if we reacted that with triphenylphosphine, that gets us the salt. Then we can deprotonate that with base and butyl lithium. That's the Wittig reagent. And then that will do the condensation to install those 3 carbon atoms. So what's on the last slide here? That was, any questions? Timed that just perfectly. So on Wednesday, what we're going to do is one more addition reaction to oxidation state 2 with a reagent we've seen before, but that's going to take an aldehyde or a ketone and now make a carboxylic acid or an ester, and then from that we'll make all the derivatives.